Hello everyone and welcome to today's theory prep video. Today we'll be talking about understanding longer proofs. So let's first talk about strategy about how to read proofs. So when you read longer complex proofs, you will almost certainly have to read them multiple times. And the first time you read it through, you should just be reading to get sort of a proof idea. It's totally okay to not understand every sort of little detail in every single part of the proof, but you really should just be reading sort of get the intuition behind the proof. In other words, you should be able to sort of summarize the proof in a couple of English sentences, and actually I'd recommend doing that. It's a pretty useful exercise to make sure you understand what's the outline of the proof. And that's really important because if you understand the outline of the proof, then when you're looking at all the little parts of the proof, you'll be able to sort of contextualize them and see why they're important. So you'll be more motivated to learn them, and you'll also understand how the pieces fit together, which will help you just in understanding all the mathematical details as well. So then your second and third time, the other times you read the proof, you can fill in the mathematical details and understand the proof in more rigor. And feel free to come back to any parts that are still sort of causing you trouble, or sometimes it's good to just take a break and come back to the proof later. That can help your understanding. So we're going to go through an example proof today and apply some of these strategies. So the proof that we're going to talk about today is pretty surprising, which is that we can calculate any finite function, or we can compute any function in NAND. So to read you it, it says, there exists some constant c greater than 0 such that for any n in m, where n is the sort of size of the input binary string and m is the size of the output binary string, there exists some NAND circuit program with at most c m 2 to the n line. So there's a bound based on sort of how big the input and the output set are that computes the function f. And that's really interesting because that means that NAND can compute any finite function. So it's extremely powerful. And this is probably not something that you would expect. So really sort of the 0th step to understanding a proof before you even read it is making sure you understand the theorem as well. So here what we're saying is, any function, no matter how it's defined, whether it's like an XOR or a majority or various other types of functions, like NAND can compute that. So if it still seems a little bit unclear to you what this is saying, maybe take a second, try out some examples, make sure you really understand it before moving on to the proof. Because if you don't understand the theorem, you definitely won't understand the proof. Great. So let's talk about the proof idea. So first, note that for any function, if you have some function f that maps from 0, 1, n to 0, 1 to the m, well, we can really just write that as like f sub 0 maps from 0, 1, n to just 0, 1. And you can have a bunch of these functions, and eventually you have like f sub m minus 1, which maps from 0, 1, n to 0, 1. And so this is to say, if we can show how to compute some function that maps from n-length binary strings to just single-length bits, then we can just we can run sort of m of those programs, right? So in particular, the theorem says that the NAND circuit to compute all of this will have c m to the n lines. So if we can prove that we can compute some function f0 in c times 2 to the n lines, well, then we can just compute that one in c to the n lines, and we can compute f1 in c times 2 to the n lines, et cetera, et cetera, et cetera. And overall, it'll take c times m times 2 to the n lines. So we're we're going to simplify the problem down to doing that. And then the second part of the proof idea is, let's think about what a finite function is. And let's take this example on the side here. So it's just some arbitrary function g, and for any input, it gives you an output, right? And so we actually see basically a finite function maps binary strings of a certain length to bits. So another way to phrase this problem is sort of a lookup problem, right? Like an equivalent problem to this g right here is you just have the string 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1, 1. And on an input x, you look up the x bit of this. So if your x is like 0, 0, 0, 0, then you would look up the 0th bit, which would give you 1. And if your x was like 1, 1, 1, 1, you'd look up the last bit, which would give you 1, right? So another way of saying, like, can we calculate a finite function is, can we just look up a bit at a certain position in an input string, right? So if we have some, like, if we're able to create some function, lookup, and this is sort of a proof outline, right? So we're not saying we know how to do it, but this might be our strategy. So if we're able to do that, then some function lookup that returns the xth bit of s, then we can just define s according to G's behavior, right? So we can define s to just be the string of like all possible things that it can output ordered from least to greatest in terms of binary value. And then we can just use lookup. So that sort of simplifies our problem down to, let's just see if we can efficiently compute lookup. And if we can efficiently compute lookup, then we'll use that to prove this result about all finite functions. Great. So now we need to calculate lookup quickly. And now we're going to go into a little bit more detail. So let's rigorously define lookup. So here's a definition from the 121 textbook. The lookup function, and remember, we're dealing with finite functions here that map from a certain size set to a certain size other set, takes in 2 to the k plus k bits, right? The first 2 to the k bits are like this string right here, the string that you're looking stuff up in, and the second k bits are like the index, so that would be like these 4 bits, which tell you which place to go in the lookup string. And it's going to be defined as follows. So for every x, which is the string to look up in, and I, which is the index to look up at, it just returns the ith index of that string. Cool. So that's the definition. Again, going back to our definition tips, right? Make sure that really makes sense to you. All the pieces fit together and match your intuition. So now we're going to prove a different theorem. We're going to prove that for every k greater than 0, there is a NAND circuit program that computes this lookup function, and the number of lines in this program is at most 2 to the k. And why will that be helpful? Because basically, we're going to use this lookup program to compute our finite function. And since the lookup program only takes 4 times 2 to the k time, well, that's definitely, we can pick c equal to 4, and that'll be c times 2 to the k time, or c times 2 to the k number of lines. And so that will allow us to successfully prove our initial theorem. So now we have sort of a sub-theorem that we're going to want to prove. So let's prove this sub-theorem. And the key idea is that you're going to be able to break up a lookup on k into 2 lookups on k minus 1. And that suggests sort of a recursive dependent structure, which implies that we should use induction. So suppose k equals 3, so maybe we're looking up in this string right here, and we're looking up in the 101th bit. And so that means we're looking for this 0 right here. And one way to address this query would be to split up this into 2 sections, and then if this first bit is 1, then take the other bits and query lookup k minus 1 on this section. And if this first bit is 0, then take these other bits, 0, 1, and query them on that section. And so you'll see correctly, if it's 101, we would get this bit, and if it's 001, then we get the first bit. And so in both of these cases, the 2 queries to look up k minus 1 will return the same thing. And so we can break up this lookup k into 2 lookup k minus 1s. And therefore, if we can prove something about lookup k minus 1, well, then that implies something about lookup k. And so we could use induction here, because induction allows us to use an implication like Pn implies Pn plus 1, and use that to imply something about P of n for all n. So let's do this induction. And to be explicit, now we've moved past the proof idea into the actual proof. And we're going to prove this predicate. And the predicate is lookup k is computable by a NAND program of at most 4 times 2 to the k minus 1 lines. And note that this implies the theorem, the original theorem, because in our original theorem, we only need the program to be at most 4 times 2 to the k lines, but 4 times 2 to the k is definitely greater than 4 times 2 to the k minus 1. So if we are able to prove this predicate, we'll have proved the theorem about lookup, not the theorem about finite functions. Great, so for k equals 1, lookup is actually just an if statement. And we can see, right, if we have some lookup 1, and we're supposed to evaluate on some x0, x1, and some index I, well, then this is just equivalent to the if function from the reading, with I being the condition and x1 and then x0. Let's put this as a subscript. So we have already done the base case here, and we know if takes 4 lines, right? And so this will take 4 lines, and 4 is equal to 4 times 2 to the, in this case, k is 1 here, minus 1. So 4 is equal to that, and so it's certainly less than or equal to that. Great, so now we've proved the base case, so now we want to do the inductive step. The inductive step is going to require discussion of breaking down a lookup k into 2 lookup k minus 1s. So again, sort of centered on our proof idea, we're going to dive into it a little bit more. So I claim that lookup k, and we're doing the inductive step for k. So we're going to be clear, we're going to assume p of k minus 1, and we want to show p of k. So I claim that lookup k on some string and some index is equal to, you take if of the first index, and if it's 1, you do this lookup on sort of the greater half, or the x's with the greater half of indices, and otherwise you do this lookup on the x's with lower indices. So how do we know this is true? Well, if I0 equals 1, then lookup k, this lookup k statement is asking for the element at the 2k minus 1 position plus sort of the numerical value of the binary string like I1, I2, dot, 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 IN minus 1, right? And that's exactly what we're getting in this lookup statement, because in this lookup statement, we've sort of added 2 to the k minus 1 to all the indices, and then this lookup, k minus 1, looks up the element in this position, which corresponds to making sure that we bump up, or that we index that far, much farther into the string. And if I0 is 0, then we want the element just in this position, right? That's how lookup k is defined. And again, we get that because we just use these. Lookup k minus 1 gets the binary value, or the like sort of numerical value of this, and looks up that index in this string, which is exactly what we want. So we see in both of these cases it works out, and they're exhaustive. So that means that we can successfully get a program for lookup k using 2 programs for lookup k minus 1 and a program for if. So the last part is just proving the runtime property, right? Proving that we run, or we only take 4 times 2 to the k minus 1 lines. So let's see how long this takes. Well, if takes 4 lines, and then we know by the inductive hypothesis that each of these takes 4 times 2 to the k minus 1 lines. So we have 4 plus 2 times 4 times 2 to the k minus 1 minus 1. That gives us 4 plus 4 times 2 to the k minus, we're just going to move this 2 inside here. So that gets rid of the minus 1. And so then we just have 4 times 2 to the k minus 2, which is equal to 4 times 2 to the k minus 1. And that's exactly what we want. So we see that the runtime is bounded below that. And so that, to remind you, now we've proved by induction this predicate, and this predicate implies this theorem here. And now, if we go back to our original proof idea, the original proof idea was basically just to use lookup to do any, or to calculate any finite function. So let's do that actual proof. So for concreteness, we'll do this proof for that function g that we had established, but clearly it will generalize to any other finite function. So first, what we're going to do is we're going to set we want some variables that are equal to 1 and some variables that are equal to 0. And so this is just sort of like boilerplate NAND code that will always evaluate this. This first statement evaluates to not x1 or not x0. And so clearly this will evaluate to 1 and that will evaluate to 0. So these are just so that you can have a 1 and 0. And so then this part of the code sets the values of the lookup string that we're going to be looking up into the correct values, right? So it sets the first bit of the lookup string to be what the function evaluates to on 0, the second bit to be what it evaluates to on 1, etc., etc. That way, our lookup is guaranteed. If we look up on the input that the user passes to us, well, it will be guaranteed to return G, x0, x1, ... So it will return G evaluated on that properly. And we'll just hard code the values of G in here. And so we know this takes 2 to the n lines, and our boilerplate code takes 3 lines. And we know that this lookup takes at most 4 times 2 to the n lines by the intermediary theory that we proved. So if you take all of this and you sum it up, it's going to take less than, say like 10 times 2 to the n lines, right? Or we're just careful and use 10 so that for low n, we outpace the constant. And so that proves our theorem because we could set c equal to 10. And we see now that nan-circ can compute any finite function, which is a result that we may not have originally expected.